Hello everyone, my name is Salman Razavi from Global Institute for Water Security. I'd like to welcome you all to the second week of this term or this year seminar series on breakthroughs in water security research. I would also welcome our simulcast viewers, in particular our students in Beijing Normal University in China who are viewing us very early in the morning at 5:30. And for our simulcast viewers, if you have questions, please send me an email before the end of this talk. So you might find my email online or salman.razavi@usac.ca, and I'll do my best to ask them on your behalf before the end of this session. And there is also a sign-up sheet over there for our students on campus who are taking this for credit. As always, I'd like to thank Jay Familiarity and Global Institute for Water Security and John Pomeroy, Global Water Futures, for underwriting this seminar series and providing logistics to make it very successful as it has been the past several years. So it's a great pleasure this week to welcome Professor Bart Nijssen to Saskatoon. Bart is Allen and Inger Osberg Professor in Civil and Environmental Engineering at the University of Washington, where he leads the University of Washington Computational Hydrology Group. He received his PhD at the same university in 2000 and then joined the University of Arizona at Tucson as an assistant professor the year after. His career path is interesting and quite inspiring, in particular, I think, to early career researchers. In 2005, just 1 year before getting tenure, as he told me last night, he decided to leave academia and go to private industry. He did it, and he did very well, and he was very successful in that. As the vice president of a company, he did work on forecasting and resource assessment for renewable energy project, and basically during his term, the company grew up, if I'm mistaken, correct me, from a handful of people to tens or about 70 people. So again, quite interestingly, he decided to come back to academia in 2011 when he joined University of Washington as a professor. So Bart is a well-known person to many of us. He's been a leading scientist in computational hydrology and modeling. Many of us know of his great work on the Wick model, variable infiltration capacity model, and more recently, he has been a major contributor to a recently developed modular modeling framework that allows different modeling alternatives called SUMMA, and he's been doing that with Martin Clark and others, our very own Martin Clark now. And I believe we're going to hear about that today. So without any further ado, welcome Bart, and I'll pass it over to you.
Thanks, Salman. That's very kind. I also want to thank Jay and John for inviting me and supporting the visit. It's been very interesting so far, and I really appreciated the talks I've had with quite a few of you today. All right, so with that, let me get started. Oh, and also, the people in China that are watching this at 5:30 a.m., kudos to you. I mean, I must say, that's pretty impressive. All right, so I hope I live up to that. So my talk will be about breakthroughs in process-based hydrological modeling, and I'll come back to the title a little later. So as Salman already told you, I lead the computational hydrology group, which actually is not as large as it may sound. It's basically just me and my grad students, and over time, sometimes postdocs, sometimes not. And so what we do is we build tools to simulate and investigate the hydrological cycle and apply that to a wide range of hydrological applications. And a lot of that involves looking at climate change and the impacts of that on hydrology. This is my group and the former members of my group. All the work that I'm presenting, they actually did most of the work on that, I have to say. So keep that in mind. None of this is an individual effort. Okay, so Saskatchewan, this apparently is the flag of Saskatchewan. I didn't quite know that. But Saskatchewan and I go back a long way. In the mid-90s, when I was actually doing my PhD at the University of Washington, even though from that work that I did at the time, I'm mostly, best known for the work on the variable infiltration capacity model and global modeling kind of applications. None of that actually ever made it into my PhD. My PhD thesis was actually on Boreas, which was the Boreal Ecosystem Atmosphere Study, which was a field experiment, and part of that field experiment was here in Saskatchewan, just north of Prince Albert, which was called the Southern Study Area, and the Northern Study Area was north of Thompson, Manitoba. It consisted of a series of flux tower sites, various kind of vehicles to make yourself through the black spruce bogs and so on. And it existed of a lot of remote sensing. So some people described the project at the time as a bunch of airplanes looking for a project. But, so I was on the website of Boreas to get some pictures, and this happens when you archive a website and then still make it accessible 20 years later. This is the photo gallery as of today. So anyway, so be careful when you archive websites is the point. All right, so my talk today is about breakthroughs in process-based hydrologic modeling. And as I was kind of like, the title is partly assigned a little bit, so I was thinking about this because breakthroughs by definition don't happen all that often. I would say if you have 1 or 2 breakthroughs in your career, that's probably a good, a pretty good batting ratio. So instead of like focusing on the breakthroughs in process-based hydrologic modeling, I actually decided that I would focus on what I actually spend most of my time on. And it's really kind of enabling like hydrologic modeling and maybe myself and others to kind of get some of these breakthroughs. And so it's much more about like the infrastructure that we often do not explicitly address when we're talking about a lot of these projects. Okay, so process-based hydrologic modeling. What am I talking about here? Well, some processes are pretty interesting. I was actually spending quite a bit of the summer at NCAR, which is here in Boulder, in Colorado. And on the way back, I actually drove there this year instead of taking the plane, and we were driving back, and we decided to go through, Yellowstone and so on. And we stayed in this little place here called Afton, Wyoming. And Afton, Wyoming is known kind of for 2 things. It's a tiny town, so it's not known for a lot of things. But one of them is that it has the largest arch made out of elk horns in the world, apparently. It includes about 3,000 elk horns. So that was the one thing. The other thing, though, for hydrologists might be more interesting. There's an intermittent spring in Afton. So what does that actually look like? So it's a nice little trail to go out there. And so this is actually the spring. The spring starts up here in the mountains, flows downhill, obviously. And if you, this is a picture, I took a little video, but like, I don't want you to sit through 5 minutes of video. So I'm going to kind of show pictures of this flow in this little stream at 1 minute increments. And if you do that, like as you stand there, this flow actually increases. And it actually becomes like a real little stream. And then after a few minutes of doing that, it actually stops again. And like as the little sign says that the USGS has, or the Forest Service has installed there, suddenly the flow stops. After 12 to 18 minutes, which seems awfully precise, the water gurgles to the surface and the cycle repeats, which is kind of odd, right? Like can you actually have this stream that kind of stops running and then it restarts again? Well, they provide a little explanation as part of this. Basically, there's a cave behind the head of this stream. The cave fills with water, and the outlet of that cave actually ends up acting as a siphon. So once this water in the cave rises high enough, you get a siphon effect. It quickly empties the whole spring. The flow in this stream increases, and then as the water level drops, the siphon effect goes away, and the flow returns to normal. Apparently, there's a few streams like this around the world. So for the type of modeling that I do, which is large-scale modeling, some of these processes, they're really interesting as a hydrologist, and they were great to kind of visit as I was driving through, but they're perhaps a bit obscure. Maybe we don't really have to spend a whole lot of time thinking of them in the context of large-scale models that we develop. Although I wanted to show it because it was so obscure and it was kind of cool as a hydrologist. All right. So the rest of this talk is basically split up in 2 parts. First, I actually kind of want to show you the type of work that my group does. And then I actually want to talk about some of the infrastructure behind this and about some of the things that all of us spend a lot of time doing and that we don't often get a lot of credit for. And I'm not doing that because I'm asking for credit. I'm just doing that to kind of make all this work that happens behind the scenes visible, because you know, as I said, that's where we spend a lot of our time. Okay, so what kind of projects do I work on? As I said, a lot of it is associated with large-scale hydrology and then looking at the effects of climate change on hydrology. And so this is a project that we did in the Pacific Northwest. You know, Seattle is up here. The Columbia River Basin is the basin in our backyard, and the headwaters of the Columbia are actually in Canada. Actually, turns out that about 30% of the flow, not 30% of the area, but 30% of the water actually comes out of Canada that we see in the Columbia. And the Columbia is characterized by lots of dams. And many of these dams actually generate hydroelectricity. And so, you know, in the Pacific Northwest, about 70 to 80% of our power is actually hydropower. And so the Bonneville Power Administration, which is the agency that manages a lot of these projects, was curious about, okay, so what does climate change potentially mean for the flow in the river, since for them that actually kind of really changes the reliability of the electricity system, and can they actually kind of, you know, support going forward. And so we ended up doing a study for them where we actually followed one of these kind of, I would say these days, kind of standard modeling chain. We basically started with emission scenarios, global climate models, right? So we would, in this particular study, we took two different emission scenarios, the RCP, representative concentration pathway, 4.5 and 8.5, took the global climate model output, did a downscaling and bias correction step. If these terms don't mean all that much to you, don't worry. Not because I will explain them, I won't necessarily explain them, but they're not all that important for the overall story. And then we actually ran hydrologic models, and then the output of that can then go into impact models. And really what BPA was interested in is like the spread that they get in these model estimates of what the future will bring. Where does that spread come from? Does that really come from the differences in the RCPs? Does it come from the differences in the hydrologic models and the differences in the GCM? And so on. So we ended up creating 160 of these alternative futures, basically. And then analyze that to determine where that spread comes from. And so we were trying to analyze how much the modeling choice affects the projected change. And we looked at different hydrologic variables. One of these, for example, was the centroid of timing. And the centroid of timing in this case we defined as the date that half of the stream flow passes the gauge. Right? So in the Pacific Northwest, stream flow is strongly snow melt dominated. So somewhere around like May, half of the flow passes the gauge. And then we looked at how that changes as a function, how that would change under climate change. And so, for example, in this case, with respect to this particular variable, it turns out that the RCP, which is the yellow area, and the GCM accounted for most of the variability in that 160 member spread, right? Hydrologic model had some influence, about 20% or so, and then in this particular case, downscaling and so on didn't really matter all that much. But it does actually matter which variable you look at. So here we actually have, again, the Columbia River. All the dots in this picture are all the different flow locations that we actually made these projections for. The size of the dot basically indicates the amount of flow. So the big dots kind of trace the main stem of the river. If you look at the centroid of timing on the left, it's basically the RCP for most of the sites that's most determining. There's some areas in the upper part of the basin for which the GCM is more important, and there's a few sites for which the hydrologic model is more important, but not that much. If you look actually just in the bulk change in the flow, it turned out that it was either the GCM or at some places along the main stem, it was actually the hydrologic model. And if you looked at low flow estimates, so the 7Q2 is actually the 7-day low flow in a 2-year period. So you look at every 2-year period and you calculate the flow during the 7 days with the lowest flow. So it's a low flow measurement, not measurement, metric, right? So actually for low flows, the variability between all the different methods did not come from the GCMs and did not come from the RCPs. It actually came from the different hydrologic model implementations that we had, right? So and so then we actually provide all this information to the Bonneville Power Administration, and they then take that and do their own water resources modeling with that, right? So they run actually like reservoir models and so on. All right, another type of project that my group has been working on is basically to look at human impacts on river thermal regimes under climate change. And this we actually have been doing in the southeastern United States. So in this area, we're actually working with people at Carnegie Mellon and so on, who are actually taking the output of what we do and then look at what that means for changes in the power sector, like in electricity generation and electricity demand. So we just do the water part of this. And so the southeastern United States, the reason we picked this region was that they all fall within the same electricity distribution area. So like their grids are interconnected and so on. And so it's a large river system. It's actually multiple river systems combined. There's about 271 reservoirs, and you really do have to account for the effects of reservoirs on river temperature and so on. And to actually make that happen, we again have a fairly complicated kind of model chain. In this case, we create meteorological forcings. That's that METSIM part at the top. We use that to run a hydrologic model, in this case VIC. We then pipe that into a runoff routing and reservoir operations model called Mozart. And then we take all that and we then take the output from VIC and from this river routing model, and we put that into a water temperature model called RBM, right? The only thing, there won't be a test on the details of these figures. The only thing to remember here is like, these are kind of complicated model chains every time. And then what you can do is produce pictures that show, for example, what the mean summer temperature is for the historical period, accounting for reservoir effects. In this figure, the triangles actually denote reservoir locations. And you can see that in some cases, reservoirs actually, so we're zooming in on a part of the domain here. In some cases, the reservoirs actually don't really affect river temperature in the stream at all. Like, the temperatures are the same, the reservoirs are the same temperature as the river. But in other sites, you actually see that reservoirs cause a big change in temperature. For example, on this other part of the river, you could see that the reservoirs, these triangles, have a much lighter color than the river system. And basically what happens is that if you have a large and deep reservoir, the reservoir actually stratifies, meaning that it actually develops a warm top layer and a cold bottom layer, and it does that in spring. It sets up, and then because the density of hot water, or warm water, I shouldn't say hot, warm water is lower, this is actually very stable, like layering. And so if you now actually end up pulling water from the bottom layer, that water is much colder than the water of the river as a whole. And so, as you can see here, the depression in temperature downstream of these reservoirs can be quite large. And then again, like just as in these other studies, we then can see like, okay, how much does regulation actually affect river temperature? So here you can actually see the cooling effect of some of these reservoirs during summer periods for the historic case. And then we can actually see what that does on the climate change. All right. I'm going to give one more example of what I do, and then I'm going to get into kind of, I wouldn't say the main part of my talk because I'm already halfway in, but about my main topic, I would say. Okay, so one more thing that my group has been involved in is actually with a coupled regional climate model called the Regional Arctic System Model. In this particular case, we're actually running a pan-Arctic domain, and and again means like a large team of people. It's me, it's people at the Naval Postgraduate School who do the ocean and the sea ice. It's people at the University of Colorado who run WRF as the atmosphere model. And in this case, the land surface, the atmosphere, the ocean, the sea ice, they all run at the same time, right? So it's not like an offline coupling where I take the output from one model, put it into the next one. Every time step, all these domains coordinate with each other. All right, so we have a coupler, basically something that exchanges the fluxes from the different models. Then we have the land here at the bottom. The land, basically the brown arrow, gives certain fields back to the coupler. They go to the stream flow. The stream flow comes back to the coupler, and it gets fed into the ocean and so on. So you can follow all these domains independently. And the coupling happens every 20 minutes in model time, right? And so then we can actually look at things like the Arctic freshwater budget. This was Mark Cerise actually in 2006 made a picture like this where you actually can quantify all these different sinks and fluxes between the different basins the land, the ocean, the atmosphere, and so on. And we can then make, things like this where we actually compare our estimates with other, and RASM actually does reasonably well, and then we can hopefully use that to do other type of studies. One thing that we use RASM for currently is actually make seasonal sea ice predictions. Okay, so the common threads in all these applications are basically that they consist of large teams, right? None of these projects are projects that are done exclusively by my group. In all these, we're just one player in a larger group of people. And I think like for a lot of projects in hydrology, that is becoming more and more common, especially when you do large domain hydrological modeling. The other part is that a lot of these projects involve big computers. And in the case of RASM, they actually may look like this. This is a DOE computing facility. The other project may not be quite this large, but computing actually is a really big part of all of these projects. There's lots of output. And, lots of output, I'm not talking about the quality or there's just lots of numbers are coming out of these models, right? And kind of archiving that, wading through it, and kind of like deducing what's actually important here is actually becoming kind of an art in itself. It's, running a model is one thing, then kind of figuring out like how to summarize and analyze that output and provide a message to somebody like the Bonneville Power Administration actually takes a lot of effort and a lot of time. And then the other part is that we have really complex model change in a lot of these models. And it doesn't really matter all that much whether it's a coupled model, like I showed you in the case of RASM, where all this coupling actually happens in real time, or whether it is these kind of offline coupling, where one model feeds its output into the next series of models, and to the next series of models, and so on. For all these, there's often a lot of work actually ends up being expended in kind of making this coupling happening, right? I mean, this is a cartoon from XKCD, which is pretty funny, actually, if you go there once in a while. But so this is the universal converter, right? And sometimes I feel like that as a hydrologist. Actually, even when I was doing my own PhD in the 90s, I was convinced for a while that hydrologists, what they do is rewrite file formats. Because it seemed to be that I was spending an awful lot of time at the time trying to get the output from one model into a different one. Okay. All right, so much of the time, of the research time that we're actually doing, is not really spent on thinking about the science and so on. A lot of the time on a daily basis is spent in just kind of managing the model process. And we don't really talk about that a whole lot amongst ourselves. And therefore, a lot of duplication happens as well. I bet you, like, if we went around the room, everybody here in the room has certain tools that everybody else has too, except everybody has a different version of it, and spend a lot of time trying to make sure that it produced the right answer. And so, and the time is really spent in these kind of things, like model coupling. Like, again, either offline or online, it doesn't matter, like getting output from one model into another model, it involves a lot of work. Code management, right? Hopefully you do code management. For some of us, code management consists of adding .old at the end of the file name, or v1 and v2, and then later on, then you have to, like, look, since you already used old, now you have to use not quite so old, right? And so that's probably not how you should be doing code management, but if you do that, at least you're doing some kind of code management. All right. The other part is like all these models require forcings, and these forcings never come in a way, in shape, or format that you actually need, right? There's always a lot of, as I say, data wrangling, like, model parameters. Before you kind of get to that science question that you really want to answer, in many cases you end up like struggling, like, okay, this obscure parameter in this model, what should I use as a value for that? And if I don't have a good value, then I may have to calibrate it, which then ends up being a side detour in your project of 2 to 3 months, where you now try to hook up your model to a calibration software, or you write your own, which we are, I'm sure there's many people in the room have some version of calibration software to actually make that happen. Then there's just the data management, and it depends a lot on these simulations, but like for the BPA simulations, we run 160 daily time sequences over a large domain. It ends up being many terabytes of data. If you run something like RASM, which is this coupled modeling domain, where you now suddenly have an atmospheric model and an oceanic model involved, and these models have many layers in the vertical, like, at the land surface, our data volumes aren't that large, but like, you end up easily in the tens of terabytes or more, right? And then the last thing is data sharing. In many cases, even these days, it's not that easy for me to get a file to you. Actually, Saman wanted to get my presentation, and I said, like, I don't have a USB stick. And most of the model output we're talking about here doesn't fit on USB sticks. Okay, so all of this takes up a large amount of time, and there's often not much credit with this, right? Like, and it goes at all levels. It's like goes from, if you're a grad student, most of the time your advisor will be fairly impatient with the time you're spending on any of these tasks, because this isn't necessarily contributing to that science question that they want to answer. And the same is true on at every level. Like, from me towards the funding agency, you cannot get money in most cases for doing model development or methods development. They want to see this kind of science application, right? And the kind of the one that you can publish in Nature or WRR or GRL or wherever you're publishing. All right, so that's why I'm talking here about enabling breakthroughs in process-based hydrologic modeling. I'm not actually going to tell you oh, I found this one thing. If you try this one thing, you too will be successful. I don't have that. There's no breakthrough here to show you. But I think if we as a community become better about doing some of this behind-the-scenes processes, maybe we can enable each other or other people in the community, or maybe even yourself down the road, to achieve some of these breakthroughs. Okay, so what am I talking about here? Some of that is actually very simple. Software best practices, right? Actually, one of the things that I took with me when I came from the private sector and went back to academia was software best practices. At the time, as Saman was saying, I worked in the private sector for about 5 years. We went from a company of about 10 to about 70, not really due to my talents, but that's just kind of what happens. And the people that reported to me were kind of the infrastructure part of the company. I had system administrators, software developers, and so on. And software version control was just kind of ingrained with them. It wasn't kind of oh yeah, after the fact, we should spend some time doing some version control. Which old version goes with this version, right? They, from the beginning, at the start of the project, the first thing they would do was set up a version control system, right? And I took that with me when I came back to the university. So this is, for example, the GitHub. So GitHub is just a website that helps you doing version control. There's different version control systems out there. Git is one of them. GitHub just kind of allows you to interact with it. It's actually kind of a nice site and so on. And so we use it in my group. So this is actually the group for the GitHub site for my group, UW Hydro. And for Vic, we actually have the Vic history, because fortunately, even before we put it on GitHub, people had been using older version control systems like RCS and so on to keep track of the code. And so we actually have commits that go back all the way to the mid-90s. We have 105 releases of the code. We know exactly who contributed and so on, right? And we can actually kind of retrace. If you say hey, I ran this version of the code and something went wrong, we can actually go back and see what that means. We also have documentation. Now the documentation, I would say, keeping the documentation in tune with or synced up with the code is sometimes challenging. And nobody pays you to write documentation. The only reason to write documentation is so that somebody asks you a question about your model and you could say, go read the documentation. After that, you can ask me a question about the model, right? But it really also helps, in my own group, new people coming into the group and so on, they have a place to go. They can kind of look at stuff. As part of that, we also, you can actually create DOIs, so what's the D stand for? Object identifiers. So basically, these are kind of all your papers, right? They come with a DOI. And so you can point to that DOI, it uniquely identifies where to find that particular version of the paper. You can do the same with code. So we actually mint the DOI every time we create a current release, and we actually say in the paper which version of the code we used. And we do that by identifying the DOI. All right, so software best practices, version control, Documentation for users and developers. We're actually terrible about having documentation for developers. Like, you know, the standard joke is like, well, the best code is the best documentation is the code, which isn't all that helpful for a developer. Testing, like, so, you know, when we make changes to the code, since we use GitHub to do this, every time we make a change to the code and we commit that change so that it becomes part of the repository, it automatically spins off a whole testing procedure. We don't have to do anything for that. It just like it happens all behind the scenes, it happens in the cloud. We have to set it up. But that way, at least we can make sure that the model compiles, it produces some output, and we can even check in some cases that the output is meaningful. And then the other thing is open source. And as a community, I think that's really important. Most of the journals these days require you to actually, you know, provide the data sets that were used in the creation of the particular paper. But also in many cases, they now want to see the code that you produced. And so, you know, that you have a place to point to. So that's one thing. So best software practices. Model coupling. So as I said, a lot of these models, a lot of these model applications involve very complex modeling chains, right? We have like, we're trying to connect, I mean, we don't really often connect the HDMI to a diesel, but some of it sometimes feels like that. And so if you actually look at models, right? So I actually, like last night, I was like putting the final slides together for this talk, and I thought like, okay, so how much of the source code in Vic has actually to do with physics, and how much is really just like reading files, moving stuff around, and so on? Well, it's like this. About 40%, 35, 40% of the code is physics. All the rest of the code is just kind of making sure that I can read input files and I can write input files and so on. And maintaining this actually takes a lot of work and a lot of effort, but it's also what kind of makes the model useful at the end of the day, right? And so, okay, so these are the slides that I didn't realize earlier. Okay, so this is again, this is RASM. And I'm just going to say here, like, so RASM, we basically need to communicate with this coupler. And so we have this coupler in the middle, and it's kind of like the director, right? It says like, okay, now you run, and here's the fields you get from the other models. Now you run, and then it coordinates everything. Vic actually was originally not coupled in this kind of a framework. And so when I actually ended up inheriting this project from somebody else. And it was like, okay, well, the proposal says we're going to couple Vic in there. It ended up taking us like forever to actually make this coupling happen. It was not straightforward. This was actually the crying emoji. It comes and it's a crying emoji because it took us, as I said, it took us a really long time to do this. And I'm not entirely sure that at the end it was really kind of a good use of our time. I think the better use would have been to take the hydrological model that was already there, which was CLM, and actually improve its hydrology to the extent that we needed to. And so and again, like, you know, we had committed to do so, and therefore we will. So we did, and we rewrote half of Vic, and we rewrote all that plumbing code in the model to actually make it possible to run in a different way in this framework. None of that is easily publishable. Okay. And so, you know, as I said, this model coupling happens in many different ways. It happens in coupled models, but also in these kind of offline model streams. And you kind of have to make sure that formats match, time stepping matches, and all that stuff. And, you know, hydrological models or land surface models have become more and more complicated over time. If you look in the 70s, the focus was mostly on surface energy fluxes, but now we're trying to represent plant canopies, heterogeneity, dynamic vegetation, carbon cycles, nutrients, and so on. So this coupling problem isn't going away. It's actually becoming more and more important. And so when you kind of develop these model infrastructures or these model frameworks, it's really important to keep in mind early on that this coupling can't really come after the fact like we did in this RASM project. Okay, multi-model frameworks. So this is a paper that came out earlier this year. It was by Nans Ador and Lieke Melsen. Nans is in England these days, and Lieke is in the Netherlands. And they actually looked, what they were doing is they basically did a literature survey, but they did it kind of in a data science. They didn't actually read the papers. Well, they may have read some of the papers, but they basically looked for certain keywords in the hydrologic literature and then used that to classify. That's what they analyzed their based their analysis on. And so the paper was called Legacy Rather Than Adequacy Drives the Selection of Hydrological Models. And so they looked at 7 different hydrological models: VIC, PRMS, GR4J, HBV, SAC, MHM, top model. And then they looked at a bunch of different institutions, including the institutions where these models originated, and then kind of looked at like what fraction of the publications actually were written with a specific model, right? And perhaps not surprisingly, we're actually in this list here is the University of Washington, UW Seattle. And, you know, a lot of our publications, 90%, that they analyzed used VIC as the model. Perhaps not entirely surprising, right? Similar, Princeton, because Eric Wood was at Princeton, right? Dennis Lettenmeyer was at the University of Washington. Eric Wood was at Princeton, so those 2 instances used a lot. And then there's actually some Chinese institutions that also ended up using a lot of VIC. And they tried to kind of figure out where that came from. And so like this figure basically shows that a lot of VIC was often the origination of the arrow shows where the study was done, and the where it points to is the application domain, right? So a lot of the studies were done by people in the US for studies in the US. The same actually for China, and actually also there's a fair number of Canada up there too. And so what they were actually looking at is like, okay, so are people selecting this because that's the best possible model for a specific location? Or are there other reasons why people select certain models, right? And not surprisingly, familiarity plays a big role in picking models. And that's not necessarily a bad thing, because if you're familiar with the model, you also kind of know where its weaknesses are, where you should not be applying it, and so on. And it actually turns out that if you look at like a lot of these applications in China, are partly because some of these people spend time at the University of Washington or at Princeton working with either Dennis Lettenmeyer or Eric Wood. And also because, you know, VIC actually kind of, it was easy to set up. It only required the plain vanilla C compiler to run. You can run it on small computers, big computers, and parameters and forcing data sets were readily available for large domains. Okay, so familiarity was one, and model ecosystem was another. And so model ecosystem to me is like everything that's not the actual model code, but all the other pieces that you need to run a model. It's the part that we don't really talk about all that much, but actually takes most of your time, right? So Lieke and Nance in this particular paper actually then end up kind of advocating for multi-model frameworks. Multi-model frameworks are basically the ones that let you configure different type of models or different type of setups using the same model code, with the idea that some of that model ecosystem stays the same for different types of model configurations that you're using, potentially reducing the time that you spend kind of like configuring your model. So it would make it easy to switch between model structures, because that's kind of built into these multi-model frameworks. You can actually construct controlled experiments. Controlled experiments in the sense of, because everything else stays the same, if I change the single model parameterization, I can actually isolate where differences between model results come from. It facilitates the incorporation of new insights and knowledge, because potentially, like if you actually spend the effort on coding up a new parameterization or a new algorithm, you can use that in many different kind of settings. And then it stimulates pluriformity in modeling approaches. And one example of this would be SUMMA. I mean, it's definitely not the only one. NOAA MP. NOAA MP is basically a version of a multi-modeling platform. Jules, used in the UK, is kind of an example of this. But this is one that Martin Clark, who is now part of the Global Institute of Water Security, has been working on, and I've been working alongside him for the last couple of years. And basically here the idea is that we have a solver that solves the thermodynamics and the water balance equations in a consistent way, but then we can actually select different ways, like these green things at the edges here, of parameterizing individual processes. So we can, for example, say like, okay, if we look at water flows through snow, we want to do gravity drainage, or we do instant outflow. Basically, if it melts, it shows up at the bottom of the snowpack and so on, right? And we can actually isolate where these differences in model come from. In SUMMA's case, we can also kind of configure the model in different ways spatially. So you could treat it as a bunch of individual grid cells, kind of like how VIC or some of the other large-scale models are running. But you can also allow for exchange through a saturated aquifer, or even where different soil columns contribute to a common aquifer, or you can actually allow exchange between individual model elements through the saturated zone. Okay, model ecosystems. As I said, to me, model ecosystems are basically everything other than the model code itself, right? We can actually, this is the SUMMA driver in this case, but models consist more of just this model code, right? I can tell you, you say like, oh, I got this problem, I need to set up a model and I want to, I don't know, come up with a problem. I want to study prairie pothole hydrology in the Saskatchewan plains and so on. And I can tell you like, okay, here's a model code. It's not of particular help if that is your problem, right? Without like forcings or ways to generate forcings, without parameters, without analysis scripts, that model code is just all it is. It's a bunch of text in a text editor, right? So parameters, forcings, workflow, and analysis are really all part of this model ecosystem. And so we really need to come up with ways to better share these model workflows, document these model workflows, and actually in some ways you really want to treat the model workflows themselves as a real piece of software that you're writing and that you need to version control. I mean, I'm actually like, I'm reasonably savvy at kind of like version control and so on. I bet you I would have a hard time reproducing the results for my papers that I did for my PhD. Not because I can't find the model code, because that's version controlled, but like all these workflows that like, how do I derive parameters from base fields? Like, I have a vegetation map, how do I transfer that into parameters? Those codes, I'm not sure that I still have those. I doubt it, to be honest. Right? So that consists of four things: parameter, workflow, and the analysis that you do on these models. Now, there are some initiatives in the community to actually work on this. HydroShare is a project that David Tarboton at Utah State University runs. And it really is an idea to kind of create a site where people can store and share data, publish data and models. So in this case, publishing means that you get a DOI for that particular version of your data. You can access hydrologic data and models, and you can collaborate. And this is not the only example, but I'm just kind of highlighting this as like people are working on this. And it's kind of this behind the scenes kind of grunt work that as a community we often don't really give each other credit for, even though each one of us spends most of their time doing actually this kind of stuff, right? The other one is accessible computing infrastructure. More and more, these model applications end up being much larger than you can run on your local machine or on your local laptops. And there are many ways to kind of go about this, right? One way is to get access to big computers. And most of the big computing centers, at least in the US, I'm not entirely sure how it's arranged in Canada, but you can actually get grants. In the same way that you can get money grants, you can get grants of core hours. Like, you have a project, you need computing time, you can write a little proposal, and they will give you 400,000 core hours or something, whatever you need. Well, up to a point, I'm sure. But the other route that actually is being followed is actually to start running some of this stuff in the cloud. And so Pangeo is a collaborative effort. It's a project you can go online, pangeo.io, and one of my former graduate students, Joe Hammond, who actually worked on some of this RASM stuff, he's actually been very active in this community. And the idea here really is to foster collaboration around open source software. In this case, it's scientific Python, but it doesn't have to be that. But create an ecosystem for ocean, atmosphere, land, and climate science, right? They also then support the development of domain-specific packages for these, but they also try to get improved scalability of these tools. So these are analysis tools and so on, so that you can actually handle petabyte scale, 1,000 terabytes data sets on high-performance computing and cloud platforms. And so part of that cloud platform is that you can actually run your models in the cloud then. And we've been using that, or I've been using that for some of my classes, where I actually have SUMMA set up in like Pangeo, and people can run SUMMA from inside their Jupyter notebooks. And I've actually been using this in classes for people to do projects and so on. And the nice part is, like, I used to do this where people like would compile SUMMA locally on their machine. Well, that doesn't work because SUMMA is programmed in Fortran, and It's a nightmare. So then we use Docker. For those of you familiar with that, that was still a nightmare. And actually being able to run it in the cloud, the nice part is that I have complete control over the computing environment that people are using, and they're all using exactly the same one. So if they run into a problem, I can actually reproduce it. Okay, the very last thing that I want to talk about before I wrap up is the other thing that we need, and I haven't really talked about this in earlier parts of the talk, but one thing that we really need is observations at scale. And what do I mean by that? If you're a large domain hydrological modeler, you typically end up having a variety of products to compare your model output against, right? And some of those are actually observations at scale. If you look at streamflow, that's actually the accumulated response or the integrated response of the whole upstream area, right? But if you're trying to look at soil moisture, a soil moisture measurement, is the size of a hockey puck, and it's hard to relate that to your 10 by 10 kilometer model element or your, even if you have a few hundred square meter model element. So really what we need to start doing is looking at observations at scale. And Jay has been doing some of that work by using the GRACE data. One of my students recently did a project where we actually took output from SMAP, which is a soil moisture mission, and GPM, which is also a satellite mission, but it's like satellite precipitation. So the first one gives you soil moisture, the second one gives you precipitation. The problem is it gives you only soil moisture in the top 5 centimeters of the soil. But even so, the idea was this, what could you actually deduce about hydrologic dynamics if you just take this satellite output? And in this case, we're just looking kind of at the decay timescales of soil moisture in this top 5 centimeters. And so this is kind of like the characteristic time here. So it's on the order of a few days. But what we can then do is kind of take model output and actually say what our models predict, right? And what we now have is actually observations taken that somehow represent a 10 by 10 kilometer pixel. And we have model output at the same scale. We're not trying to upscale a local specific measurement to a larger area. And we actually need much more of that for continental scale type modeling. All right, so that's what I mean. So rather than talking about breakthroughs themselves, I wanted to talk about the things that enable these big breakthroughs, potentially. So software best practices, model coupling, multi-model frameworks, model ecosystem, accessible computing infrastructure, and observations at scale. And then we really should be sharing all of the above, right? And having platforms where we can do so. All right, so the last thing is that I really appreciate the opportunity to visit here. But I also think that, with the amount of talent that's kind of located here in GIWS and in GWF, as a group, you have become a little bit of the 500-pound gorilla in the room. I mean, we're having discussions about this earlier, and it was partly that, in the US, there's a lot more money going around, but it also gets spread pretty thin among many different agencies, among many different research groups. I think this is actually one of the few places where you have that many hydrologists or people with an interest in water in the same place. And so, I think with that, you can also kind of probably direct your own activities and the activities of some of the others towards practices that support some of the things that I just talked about. And so I think you really should use that power and probably wield it friendly. But I think there's a real kind of critical mass here for making some of these changes happen. And so with that, thank you.
Thanks very much for this stimulating talk. So we have time for questions from gorillas. Sorry.
Yeah, that was the risk. I didn't.
You calling me a gorilla?
No, of course not. Yeah, I'm sorry.
Thank you, Bart. That was an excellent presentation, and very salient points. In terms of enabling these enabling processes, right now you described a situation where everything is very distributed amongst everybody, basically, the grad students, the postdocs, the researchers, the operational folks. Everybody has a role, or everybody plays a role, whether they want to or not, in enabling these breakthroughs. Would you say there's maybe a better way of structuring things to better enable breakthroughs, and then what sort of responsibility, or where would that responsibility lie?
Yeah. So yes, I do think there are better ways that we can kind of organize ourselves, but I think it's also kind of a pretty slow process. I don't think there's one magic solution that if we all kind of start following this particular pathway, we'll get there. But as we talked in our earlier discussion today, there used to be the joke that if you had 8 hydrologists in a room, you would have 10 models, right? And I think we're kind of getting away a little bit from that. And I think that is actually a good thing. The reality is that when I showed that Vic thing, right, 60% of the model code is model plumbing. It has nothing to do with the science that's going on and so on. And so maintaining these models and maintaining these model infrastructures actually takes a lot of time. And so not duplicating that kind of effort helps. So the other part that really helps is using version control, because you can actually point somebody to like, hey, this is where my code is, and this is the version I use to create that particular data set, right? And then sharing, I think as hydrologists, since we're not, like most of us, not all of us, but most of us are not software engineers from our primary kind of training, right? So we all kind of have our own habits and tricks and so on that we're not necessarily proud of, and that we therefore all feel very uncomfortable bringing out in the open. I think we need to get away from that. It's like most of my code is online. I'm sure there's like lots of warts in there and so on, but I'd rather have it out there, and maybe somebody else point it out to me in a friendly manner, than just having it hidden on my own machine. So I think we have to become more comfortable, not just showing our model output and showing our model results, but how we got there, right? And I think that's something that's sometimes hard to get to. I mean, I see the same in my students when they come in. It's hard to share code. Whereas even when I was in the private sector and we had software developers, they were not shy about sharing their code. They were also not shy about critiquing each other's code. And and they had a formal system for code review. And for the big models that we have, we do code review. I don't review everybody's individual Python script to calculate the average over a spatial field. But I mean, we do code review in my group. So.
There's a question in the back.
Yeah, thanks for your presentation. I have a quick question about your first half.
Yep.
About RISM, you actually couple quite number of models. I think that actually couples the errors at the same time. If you kind of transferring information from one to one, how do you deal with those kind of errors not accumulated?
Yeah, so this is kind of like inherent to any kind of fully coupled model. This is the same in climate models and so on. As the model is running, there isn't really a whole lot you can do about those errors. I mean, they happen. It's the reason why when we take global climate model output and want to apply it into hydrology, we have to do a bias correction, because the models may have hopefully the right sensitivity to changes in atmospheric greenhouse gases. They may actually have a bias, right? They may be way too wet or way too warm. And you have to kind of live with that in these coupled models. There's no really good ways of doing corrections for that as the model is running without kind of destroying the water energy and momentum balance. So, which also actually makes these models, in my experience, they're very different than running offline type models. But there's no easy solution there.
Other questions for Bart? John.
Bart, I really enjoyed the presentation, and I think your philosophy on modeling is very compatible with what many people have thought here for some time. So that's wonderful to see it so well described and so coherent. One other aspect that struck me as we're talking about this are the algorithms themselves. I think we have more models than we have algorithms sometimes,
yes.
At least for certain processes. And I'll give you an example that involves our two universities. So back in the 1990s, we had a student studying snow interception as part of Boreas named Noel Hedstrom. And at the same time, Dennis Lettenmeyer had a student, Pascal Stork, studying this in Washington. And we developed two algorithms, and then later with Richard Escher, we worked to combine them a little bit. And they ended up in almost all the models.
Yep.
And then some decades later, there was a forest snow model into comparison project. And they all had the same stuff in them.
Yep.
And so, or they might have one or the other, but generally they had the pseudo-combined one. And so they look the same. And so, yeah, sure, you can have 36 models, but we were comparing really combinations of two different things almost completely.
Yep.
And then it's not scientifically satisfying. So are there ways to bring really, I think SUMMA could be a great vehicle to have more than 2 options, but have 10 options for different algorithms and really do that and really try some things that are rather different there. And that's one way to drive that innovation in the process modeling. Because I think sometimes we have more models than we have ideas. So
Right. I mean, 100% agreed, right? Actually, both algorithms are actually options in SUMMA currently. But it actually is more insidious than that, right? Because for most people using these models, they have no idea which of these 2 algorithms is actually in the model, right? Because it's not an explicit decision, it's just hard-coded somewhere in the model. So I totally agree that like the, I don't know, hundreds of hydrologic models that we have out there are based on a fairly limited set of physical routines, right? I mean, like most of us, like there's only a couple of ways that we're doing drainage through the Vado zone and so on. And I think part of it is like, as a community, and I think we're moving that way partly just because the cost of computation is getting higher, like just the models, end up taking more time. I think we are moving where it becomes easier for people to say like, look, I'm not going to roll my own model and start from scratch because I know how to program better than so and so. That may be true, but it actually probably is better if we can work as a group to improve a limited set of models, right? And the advantage, and I'm not saying that has to be SUMMA. I actually don't really have a great stake in whether it's SUMMA or any. None of these models get royalties, so I think like as a community, kind of contributing to a smaller set of models will be better than everybody creating their own models. And I think like your group can actually help in making that happen to some extent.
Well, I think also having the intelligence, and not by meaning smarts, but the background information as to what options to choose,
right,
for that are appropriate for the environment that you're considering.
Right, and in that sense, actually, these multi-model frameworks are nice in that you can actually control, like you can actually do controlled experiments and saying what is the difference of using the Hedstrom-Pomeroy interception algorithm versus the one from Pascal-Stork, without having all the other things in the model being different, right? Because we've been doing these MIPS, these model into comparison projects for 25 years now, right? And the outcome is always kind of the same. Like, yes, the models are different, and we can't really trace where the differences come from, because the models are different in parameters, parameterization, spatial resolution, time-stepping schemes, and so on. So it's really hard to come to an actual conclusion out of any of these MIPS. Other than saying like, yeah, everybody does kind of okay. Here's the spec.
Very good.
I have a question for you, Bart.
Right.
On the water management side,
Yes.
it was very interesting to see your work on temperature modeling and the role of reservoirs and river water temperatures. I wonder how you accounted for reservoir operation itself, things like gate control, hydro picking, or seasonality, changing the seasonality of flows, all these things. Yeah,
so we actually ran, in this case, the hydrologic model at a daily time step. That produced the naturalized or the unregulated flows. And then we actually had a water resources model in which we had we didn't do, we basically had rule curves for the reservoirs. And the reservoirs were operated according to rule curves. So rule curves basically dictate that you keep your storage at a certain level in May and then a slightly different level in June, and you do releases and so on to accommodate that rule curve, right? And in addition, then you have to make sure that you don't flood everybody downstream, right? So that kind of reservoir control or reservoir management is pretty straightforward to program up. That's actually not really how reservoirs are managed, because there's optimization involved and there's like day-to-day decisions. None of that we really regarded, right? And so we actually, this paper, it just came back, we're working on the revisions, and one of the questions one of the reviewers was asking, like, how do errors in the stream flow simulation and the water resources simulation actually carry forward into the stream temperature? So my student is now doing a sensitivity analysis to kind of quantify that. Okay, so it's 4:30.
Yeah, that was a very good note to finish on, I think. So please join me in thanking Bart for coming here and for the great talk.